This one is interesting. This is digital modulation. When we talk about digital, we're talking about a lot of different ways to do digital. And these are some of the ones we'll talk about. We're really going to focus only on the first three or four. The rest start to get pretty exotic and not as frequent, but we'll touch on them briefly. So, first of all, what is modulation? That is the process of taking a voice or data signal and using it to modify a radio frequency signal so that it can carry information. So we're modifying one, one or more of the characteristics of that radio frequency signal to carry information. And what are the characteristics we can modify? Well, we can modify the amplitude. That's called amplitude modulation. We can modulate the frequency. That's called frequency modulation. We can modulate the phase. That's called phase modulation. Or we can combine two or more of the above to have multi-level type modulation. We'll talk about that. But digital modulation is the modulation that specifically deals with techniques to convey the ones and zeros of digital data. So we need to understand a constellation diagram. This is when we are modifying a particular signal in its phase, we can represent it with a phasor diagram. And so we can, I'll show this on the next slide. There's a diagram that we can represent it with a constellation. So in the sky, a constellation is a grouping of stars, and this is basically a group of stars that represent a combination of phase and amplitude. So we use an XY plane scatter diagram in the complex plane to show the various modulation points in our particular form of digital modulation, where the angle represents the phase shift and the length or the distance from the origin point represents the amplitude. So let's see a picture of that. So here is a constellation diagram of phase shift keying with an 8 phase shift keying. Now, because this, remember we talked about C4FM, how it had uh, 4 possible phase positions. Each one could represent 2 bits of data. Well, if we were to do an 8-level phase shift keying, now because there are 8 different levels, each one can represent 3 bits of data. So we have a symbol rate which is 1/3 the data rate. And in this diagram, we show the symbol or the data point 110 represented by a phase difference of 45 degrees and a particular amplitude. Notice that the amplitude is the same all the way around the constellation. So in phase shift keying, pure phase shift keying, we're not modifying the amplitude, we're only modifying the phase. But we have 8 different phase positions. And so we can represent this as 8 points on the constellation. So the cosine or the x-axis represents the in-phase carrier, and we call that the I component, I for in-phase. The vertical axis or the sine component is called the quadrature component or the Q component. And so every angle has, you know from trigonometry that every angle has a sine and a cosine component, or you could say a horizontal and a vertical component. So you may hear the terms I and Q as it relates to a digital signal. And what that's referring to is in a phase modulation system, The I is the in-phase component, and the Q is the quadrature or 90-degree component. So we can represent the angle and the amplitude by using a constellation. Has everybody seen these before? We also have a tool called an eye diagram, which is whereas the constellation is a complex domain in I and Q, the eye diagram is a time domain diagram that we can present on an oscilloscope, where we actually show the signal in the time domain, and where we have the overlapping ones and zeros that create an eye-shaped image in the middle. And the way we use the eye diagram is to see how clean the digital signal is. If the signal is good and doesn't drift back and forth in amplitude or phase, we will get a nice big open eye. However, if the signal is degraded in phase or amplitude, the eye will close and we'll barely be able to tell there is an eye. So it's a good tool for evaluation along with the constellation diagram. And some of the more advanced signal analysis monitors can show us both eye patterns and constellation diagrams. This may be a little bit of review, but it's worth talking about again, the data rate versus the symbol rate. Remember, the simple modulations represent a 1 or 0 as a single data point, but the more complex digital modulations represent multiple bits with a single data point. Depending on how many different phase angles are represented and other characteristics, we can have multiple bits like 0, 1 or 1, 1, 0. So then again, the symbol rate is the number of signaling events per time, and it is a fraction of the actual data rate. You hear the term baud, which is equivalent to symbol rate, which means symbols per second. So higher data throughput is accomplished by providing more data points that we can represent more bits with. So the more bits we can represent with a single symbol, the higher throughput we can get. So some of the common modulation types that we know: FM. We've been dealing with FM for years. It's been around forever and it will be around for a long time. It modulates by varying the RF carrier at a rate corresponding to the audio rate. P25 phase 1, 9600 bits per second, switches between 4 different carriers, and that's each symbol represents 2 bits. CQ-PSK is a type of phase shift keying that that modifies both the amplitude and the phase. So let's talk about a little bit, not a lot, about some of the other digital modulations out there. We talked about simulcast in like the very first module today, and we talked about site separation, and linear simulcast modulation is a type of quadrature phase shift keying that has a broader bandwidth. By having a broader bandwidth and a broader filter, it's more tolerant of phase delay. And that means if it's more tolerant of phase delay, we can separate our sites further apart and still recover the signal. And we talked about phase 2 P25 and the fact that there is one type of modulation for inbound and another type for outbound signaling. And the reason for that is that these more sophisticated and complex modulation schemes are difficult to implement on a portable or mobile radio, and they're expensive to produce. So they are best found on the outbound signal, where the key goal with the outbound signal in a simulcast system is to provide the minimum amount of phase delay. So we provide that type of modulation on the outbound side of simulcast. The inbound, we use a different type of modulation called HCPM, constant envelope modulation. And that's purely for phase 2. So going back to analog FM, again, most of us understand this concept that it's a constant amplitude signal that varies at an audio rate, and it varies the frequency of the carrier. C4FM, as we discussed, it is used on both P25 and DMR, switches between 4 different phases, or 4 different frequencies, each one representing 2 bits. It has a simple 4-point constellation diagram. Symbol rate is 1 for 2. This diagram is an illustration of how C4FM works. Basically, we have the center frequency represented by the light blue line. We have 4 different shifting levels, each one representing 2 bits of data. And as the signal moves, we get different audio shifts occurring. Not audio shifts, but frequency shifts. And that's C4FM used for DMR and P25. Phase shift keying. The simplest form of phase shift keying is where we only have 2 phase shifts, and 2 phase shifts is called binary phase shift keying. And the constellation diagram only has 2 data points on it because each data point only represents 1 bit. But it is used for a lot of things, phase shift keying, not just binary, but all types of phase shift keying is one of the most common types of modulation used today, used on wireless LANs, RFID, Bluetooth, things like that. So quadrature, the word quadrature means 4. So quadrature phase shift keying means that we have 4 different phase shifts that we can go to. We can do a 45-degree shift, a 135-degree shift, a 225-degree shift, or a 315-degree shift. It's similar to C4FM in that it provides 4 different points, and 4 points means we can carry 2 bits per symbol. CQPSK is a modification on that, and again, it's a 2-for-1 symbol rate. It's compatible with C4FM, requires a linear amplifier, and then that is more expensive to produce, and that's why it's normally only used on the outbound side for P25 transmitters on the downlink. The subscriber equipment, however, will be operating in standard C4FM. The thing you'll notice about CQPSK is that it has 2 things going on at the same time. You'll notice it has both phase shifting as well as amplitude modulation. So this allows greater flexibility in the symbol rate. So there's a phase shift component and an amplitude shift component. And there is a form of CQPSK that we discussed a little earlier called linear simulcast modulation. It's basically CQPSK, however, we run it through a wider filter giving it a wider envelope and therefore allowing greater tolerance in phase delay, resulting in greater simulcast site separation. So this is a comparison of some of the characteristics of C4FM versus LSM. And C4FM does its thing by shifting 4 different frequency levels, and CQPSK or LSM does its thing by shifting the 4 different phase positions. So there are 2 different ways of accomplishing the same thing, which is carrying 2 bits of data for every symbol. And those other modulations we talked about that's used in P25 phase 2, HDQPSK and HCPM. The HDQPSK is the one that's the outbound modulation for phase 2. Similar to linear simulcast modulation, you'll see a constellation with 8 data points on it, and then HCPM constellation has 4 data points on it. So these are the 2 types of modulation that are used in phase 2 P25. And the final slide for the modulation portion is something called quadrature amplitude modulation. This is not used a lot in land mobile radio, but I'm putting it in here as an example of how far you can go with this phase type modulation. So a quadrature 16 QAM or 16 QAM, if you look at the constellation, there's actually 16 different data points on there. And notice that they're not arrayed in a circle like some of the previous modulations were. And this means that they represent different amplitudes, because when they were in a circle, they all had the same amplitude on the phase component, and these have all different amplitudes. So in QAM, the quadrature means that we're modifying the phase, and the AM means we're also modulating the amplitude. And by modulating both the phase and the amplitude, we're able to get a 16-point constellation, which means that each symbol can represent 4 bits of data. So you can see the 16 and each one represents. So every time we want to represent a 1101, we know what data point that is in phase and amplitude. Okay. So it gets really complex when you're talking about different modulations and you get into the phase diagrams and the constellations. But the main takeaway about modulation is that there are many different ways to carry information digitally by varying the RF carrier using one of its components, its phase, its amplitude, or its frequency, or some combination of the above. And there are 100 different ways to modulate a signal digitally, and we covered a few of the ones that are most commonly used.